Next, we're going to talk about lines and quadratic functions, and polynomials in general a little, but let's first talk about lines. So right here we have a line, and a line is defined by 2 points. So let's take 2 points on the line. Let's call them x1, y1, and x2, y2. And right here, given 2 points on a line, you can figure out how slanted the line is. And how slanted a line is, we call the slope. And the slope can be found by looking at how the slope is defined to be how much vertical change exists in a line for a given unit of horizontal change. And of course, using division, we can formalize that. Right here we have a triangle that's actually the Greek letter delta, meaning change. So right here, given these 2 points on a line, there is a horizontal change and there is a vertical change. And the slope of a line, how slanted the line is going to be how much vertical change there is for a given unit of horizontal change. So the vertical change divided by the horizontal change. And this is going to be a constant for any 2 points you choose on the line. So you could think of it like that. Given the 2 points, you could also rewrite this formula as the change in y, so the one y value minus the other, divided by the one x value minus the other. So the slope of a line, we're going to define it to be lowercase m. That's standard. That's a lowercase m. And it's defined to be the change in y divided by the change in x, which is also the y value minus the other, divided by the x value minus the other. You don't want to flip one of these around. You want to make sure you start with the same point. You could have written y1 minus y2 over x1 minus x2. This is more standard. Of course, they're the same. You could just relabel the 2 points. So let's look at this example. Find the slope of the line containing those 2 points. Well, we have a formula for the slope. The y change divided by the x change. So what's the y change? Well, I'm going to start here. Negative 2 minus 1 divided by the x change, 3 minus negative 5. So we have negative 3 on top and 8 on the bottom. So the slope is negative 3/8. Now, the slope of a line, remember, this is going to be constant for any 2 points we choose on the line. So if instead of choosing a fixed point x2, y2, we let this point vary throughout the line, meaning let it be variable instead of a fixed point, we could use this slope equation to find a formula for a line, an equation for a line. So letting x2, y2 vary, we'll call this a remark, letting x2, y2 vary in the slope equation gives the point slope form of a line. So letting it vary, what does that look like? Well, that would look like this in that formula. Let's let y2 be a variable, so let's call it y. So instead of fixing a point x2, y2, let's just let it be xy, and we get that equation for the slope. Now that's not the point slope form of a line. The point slope form of a line is this without the fraction. So multiply both sides by the denominator of the fraction, and you get y minus y1 equals m x minus x1. So all we did here was multiply both sides by that denominator, and then I just flipped it around. I wanted the y's on the left side. And right here we have the point slope formula. Now this is a very useful form for a line, especially in calculus, because to figure out an equation for a line, which we're going to want to do, all we need is the slope and a point. It's called the point slope form. All you need is a point and a slope. We will see in week 4 and 5, well, I guess not 5, that's, oh no, week 6 is the test. We'll see in weeks 4 and 5 that there are ways we can find slopes we want. And we'll largely be given points. So if we want equations for lines, which we will want, all we need to do is find a point and a slope. much easier than finding an intercept. Notice here you could find a y-intercept if you want by distributing the m and then adding y1. But that form, we don't need that form. That form is useful if you need the sketch of a line, which we'll largely not need, maybe a couple times. Example, find an equation for the line containing these points. Well, whenever I need an equation for a line, I like reminding myself that all we need are a point and a slope. What's a point? Well, there are two of them. Let's just choose one. You can choose either one. It'll give the same equation. So I'll choose the one that's written first. So there's a point. We need a slope. Well, we found the slope over here. The slope was negative 3/8. If we didn't find it there, we'd have to do that computation here. So we have a point and a slope. So an equation, y minus the y value, so y minus negative 2 equals slope times x minus the x value. And no, you do not need to simplify that. You don't need to simplify it. You can leave that like that. We'll talk about lines many times throughout the semester. They show up all over the place in calculus, actually. But let's next talk about quadratic functions. A quadratic function is also known as a degree 2 polynomial. We'll talk about polynomials in a moment. For now, we'll just call them quadratic functions. A quadratic function has this form. F of x equals a x squared plus bx plus c. A is not 0, but it has the form ax squared plus bx plus c. And we're going to do two things with quadratic functions. We're going to sketch them, and we're going to find what are known as roots. Let's first sketch them. And what we're going to do to sketch these is complete the square, and then once we complete the square, a function like this will be in a form on which we can sketch the graph using graph transformations. So here we have sketch this, not by picking points, by using graph transformations. Sketch x squared minus 4x plus 9. Now what we're going to do is look at the thing with x's and write them as one quantity squared. Well, how are we going to do that? Well, where are we going to do it? I'm going to do it over here, actually. What are we going to do? Well, we're going to look at those pieces with x, and we're going to add a number to it, which forces it to be a perfect square. Which number are we going to add? Well, we're going to look at this negative 4. The coefficient on this x squared is 1. We're going to look at this negative 4. We're going to write negative 4 down here. We're going to take half of that, and then we're going to square that. And if you take half of that and square it, given a coefficient on x squared 1, that will give you a number you can add to that quantity, which will make it a perfect square. Negative 4 divided by 2, negative 2 squared is positive 4. So we take half of this number and square it. Now, in math, equals is a verb. It attaches what? A subject and a direct object. A equals B means A is the same as B. So right here, what is currently written is not equal. What's on the left side of that equal sign is not the same as on the right side of the equal sign. We should only use equal signs when they are correct. How can we force this to be equal? Well, you might look at that and say you could add 5 to this. I'm not going to look at it and say you could add 5 to it yet. What we can do, we needed a positive 4 from the argument I erased. We can't change this function. We can't just throw a 4 on it. We can, however, throw a 0 on it. So we take that positive 4 that we needed. We also subtract positive 4. Because right here, 4 minus 4 is 0. So if we throw a 4 and a negative 4 on this function, that won't change anything. But we also can't forget that that 9 was there. So what we did was complete the square in order to figure out which 0 we could add that would allow us to write the things with x's as a perfect square. Because now what's under that squiggly underline is a perfect square. It's x minus 2 squared. And this negative 2 you could actually see from this computation. Right there is that negative 2. So what's under the underline made an x minus 2 all squared, and the number we're left with after that is a positive 5. Well, now we can sketch that because that's just x squared with some graph transformations. So let's start with x squared. I guess here I'm using f of x. It really doesn't matter much. Just be consistent, I guess. X squared looks like this, goes through the origin. Well, what's the first thing that happens to x? That negative 2. What does that negative 2 do? Well, instead of being at 0, 0, at x equals positive 2, this will be 0 squared. So that moves it over to the right 2 units. So that moves it over 2 units. And then finally this positive 5 takes everything, it lifts it up 5. Takes everything, lifts it up 5, so 2, 0 is going to go up 5 units to 2, 5, and the rest of the graph follows as well. Now, if you're asked to sketch one of these, I doubt I would ask you one where there is an extra number in front of the x squared other than 1. But you could do that using an argument similar to what we'll do in a few moments with the quadratic formula. But you could always complete the square on these to get it into a form on which you can sketch the graph using these graph transformations. The next thing we're going to do is find roots of quadratic functions. But to do that, we first need a definition. Definition. x0, x sub 0, x naught. x0 is called a root or a 0 of f of x function if f evaluated at x0 equals 0. So a root is a value where the function evaluates to 0. Notice here, the function is given by a set of x values and y values. So right here, a root is an x value at which the corresponding y value is 0. So we can look at the sketch of a function like this and find the roots, especially if the points are labeled conveniently like that. In this sketch here, x equals negative 1 and x equals 3 are both roots of this given function, because at x equals 3, the y value is 0. At x equals negative 1, the y value is 0. You can also see that as the points, the x values at which the function intersects the x-axis. That's equivalent. But let's look at finding roots of quadratic functions. So find the roots of each function. First one, x squared minus 4x plus 3. Well, we need the values where the function evaluates to 0. So what we want to do is set that equal to 0. So let's do it. How do we solve this? Well, we can use algebra to our advantage. Because using algebra, we can write what's on the left side as a product by factoring. How can we factor this? Well, we need numbers which multiply to 3, which add to negative 4. 3 and 1 make 3, 3 and 1 make 4, so negative 3 and negative 1 will multiply to positive 3. Negative 3 minus 1 equals negative 4. So we have the product of two things equaling 0. So when will a product equal 0? A product will equal 0 when one of the two things you're multiplying equals 0. You know, if you have like 6 times 4, that's not 0. 12 times negative 38, that's not 0. 0 times 4, that's 0. 3 times 0, that's 0. So right here, this function will be 0 when one of these two pieces is 0. So Solving this equation is the same as solving this equation is the same as solving these two equations. Solving this for x, add 3 to both sides. Solving this for x, add 1 to both sides, gives us our two roots. Well, next we have this function. I guess I'll do it under here. I probably have enough room. We have 2x squared minus 5x minus 3 equals 0. Now, when the number on the x squared is not a 1, these are much less convenient. But if the number in front of x squared is a prime number, it does make it a little easier than it could be. I would imagine all, now let's say most, all is a little too restrictive. In calculus, we'll actually be solving a lot of equations like these, setting things equal to 0 and finding x, especially in chapter 4. But when you're doing those, most of the time, I'll make the number a 1. Of the times it's not a 1, most of the time it will be a prime, like 2 or 3 or 5 or 7. It's very rare, but I have asked it, it's very rare that I put a number like a 4 or a 6 or an 8 in front of them because it's kind of a pain. But when it is a prime number like 2, it does make your choice a little more clear. Because the only way you can make it 2x squared by splitting the x's is by taking a 2x and an x. Well, now we need numbers which make 3. Excuse me, negative 3. And numbers which make negative 5. Well, what will do that? 1 and negative 3 or negative 1 and 3? We need to make a negative 5, so we're going to hope that this 2 is going to help us get closer to negative 5. So if we throw a negative 3 on this, will that work? Yes, it will. With these, it actually is a good deal of guessing and checking, I think. So right here, 2x squared, negative 3, and what do we have for the rest? Negative 6 plus 1, which makes our negative 5. So we factored that, set each piece equal to 0, solve for x. In the first case, you get x equals negative half, subtract 1, divide by 2. In the second case, you get x equals 3. Now, we found roots of these. These conveniently factored. And, well, it'll be very common that the functions we have conveniently factor. If they don't, however, factor, is there a way we could find these roots? Well, the answer is yes, we could. And we can do that by completing the square. So we have this theorem, quadratic formula. The roots of a quadratic function, ax squared plus bx plus c, are given by x equals negative b plus or minus root b squared minus 4ac all over 2a. And you can see here why the assumption that a is not 0 is important for a general quadratic. Now, how are we going to find these? Well, we're going to find where f of x equals 0. And we're going to hope this all fits on these 3 boards. How do we find where f of x equals 0? Well, what we're going to do first is complete the square on this left side, well, on this function. And when we did the previous examples, the number in front of x squared being 1 was important. So what are we going to do? Well, I'm actually just going to set it equal to 0 now, and then solve. So what are we going to do here? Well, first, let's get rid of that a. Maybe I should write it so it fits on this board. We'll get rid of that a by dividing everything by a. 0 over a is 0. Well, what do we do next? Well, we follow the completing the square process on this. What do? We take b over 2a, or b over a. We divide it by 2. And we square it. And we're going to add and subtract that. b over a, the coefficient, divide that by 2, gives us b over 2a, and then we square it. So what do we get here? We get x squared plus b over ax. What's b over 2a squared? B squared over 4a squared. Remember, we can't change the function, so we want to also subtract that. And I guess I didn't fit that on this board. So all we did in going from this second line to the third line is add 0. We needed to add b squared over 4a squared to complete the square, so we added it and we subtracted it. Well, now we can write this as a perfect square. X plus b over 2a, b over 2a squared, is how we can write this as a perfect square. Well, what are we going to do next? Well, we could write these. I'm going to put them on the other side. Equals what? B squared over 4a squared minus c over a. So I knew this was going to be a perfect square. These are just numbers over here. So I move them to the other side, add this, subtract that, and that's what we get. Now, how do we solve this for x? Well, before dealing with that side, I'm just going to write this as a single fraction. A common denominator is 4a squared. So here we need a 4a, so put a 4a there. You need to put a 4a there. That gives you 4ac with a negative, gives you negative 4ac. B squared is b squared. So the the right side simplifies to b squared minus 4ac all over 4a squared. Well, now we want to solve this for x. Well, let's take the square root of both sides. Square root of the left side is that. Square root of the right side. What's the square root of the right side? I'm going to do side work over here. Well, square root of the right side is that. The square root of a fraction splits into the square root on top, square root on the bottom. So on top we have that, but the bottom, notice, is a perfect square. Because 4 is 2 squared, a squared is a squared, and we want all such values where this squared equals that, so we're going to need a positive and a negative when we take this square root on the bottom. So the left side simplifies to this, and it's more common. It's more common because of the fraction to just throw that positive negative on top. So we took the square root. Now our goal, remember, was to isolate x. We've almost isolated x. All we need to do is get rid of that b over 2a. I'm going to write that over here. So x equals, subtract b over 2a from both sides. Notice if you subtract b over 2a over here, the two fractions both have denominator 2a. So you can combine them as one fraction. So negative b, and it's standard to write the negative b part first. So we solve for x and we get negative b plus or minus b squared minus 4ac over 2a. So all we did here, there are a lot of letters to keep track of, but remember a, b, and c are just numbers. But all we did here was complete the square, and we were careful with our notation. And you could use this to find roots. Just thinking back on all of my teachings of calculus at Muhlenberg, I think in my first semester there may have been one question on a homework assignment where they had to use the quadratic formula. I don't believe I've ever tested anything where you had to use it. In other words, when we have quadratic functions that we want the roots of, you will be able to factor them. But if you didn't factor them, and if I said don't use quadratic formula, you could follow this process and complete the square. Now, lines and quadratic functions are examples of what's known as polynomials. So let's define polynomials. Definition. A polynomial with degree n has the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus everything down to a sub 2 x squared plus a1x plus a0. Now these a sub numbers are just coefficients, and for notational convenience we subscript them with the same exponent as is on x. Now this polynomial has degree n because the largest exponent with non-zero coefficient is x to the n. And quadratic functions were degree 2 polynomials. So just this last part. In case you heard a noise, that was a car driving by. So a quadratic function is a degree 2 polynomial. A line is actually a degree 1 polynomial. All lines which are functions, I should say, are degree 1 polynomials. And you can see that from the point-slope form of a line. The only thing there is if you simplify it to the slope-intercept form, it would look just like that. And we found roots of degree 2 polynomials, and we could find roots of degree 1s, but, well, actually we did in finding roots of degree 2. But finding roots of general polynomials is actually, well, it's a solved problem in math, but it was a very difficult problem for a couple hundred years. So a degree 3 polynomial, where the largest exponent is x cubed, that was, well, the quadratic formula gives us all roots of a degree 2 polynomial. And the next question is, can you do that for degree 3, degree 4, degree 5, and so on? And in, I believe, the 1400s, there was a mathematician, an Italian mathematician named Cardano, who figured that out for degree 3. And it's a very complicated formula. Later on, someone else, whose name I don't know off the top of my head, figured it out for degree 4 polynomials. And it was a much more complicated formula than even the degree 3 formula. And then the next question is, could you do it for degree 5 or greater? And the answer is no. There is no general formula for the roots of a degree 5 polynomial. The real roots of a degree, well, I guess the complex roots of a degree 5 polynomial or greater. Now, to prove that, you actually need to know what is known as Galwa Theory. Galwa, G-A-L-O-I-S, named after the French mathematician Évariste de Galois. And he showed in early 1800s that you could not do that for a degree 5 polynomial, and his work also showed you couldn't do that for any degree larger than 5. Galwa theory is usually, if you take the advanced undergraduate math classes, Abstract Algebra 1 and Abstract Algebra 2, also known as Modern Algebra, one of the last results at the end of the second semester is on Galois' work on degree 5 polynomials. It's quite complicated, but it's not part of calculus. The polynomials we'll talk about, well, we'll see polynomials of many different degrees throughout the semester. Mostly degree 2, we'll see other ones. Now, some other functions that we could see. Rational functions. A rational function is of the form p of x over q of x, where p is a polynomial and q is a polynomial. Now, a rational number is a fraction, reduced fraction. A rational function is a polynomial divided by another polynomial. And we could find the domain of a rational function. The domain of a rational function, remember, the domain is the set of inputs. Into a rational function, you can input anything except where the denominator is 0. Domain of a rational function is all x values where q of x, the denominator, is not equal to 0. So let's look at this example. Find the domain of this rational function. Well, we need to find where the denominator is 0. This is 4x minus 5 over x squared plus 5x plus 6. So let's find where the denominator is 0. We want to set that equal to 0. Does it factor? Yes, it does, because 2 and 3 make 5, and 2 and 3 make 6. This equals 0 when x equals negative 2. This equals 0 when x equals negative 3. So we found where the denominator is 0. Did that answer the question we were asked? When you do any questions in math, you should always, after you think you're done with your work, just look back and make sure you're actually answering what's being asked. And here, we're not. Or here, we haven't. We need to find the domain. And I'm going to write it over here because I have room over here. So the domain, I usually don't write lowercase d the way I wrote that one. Felt strange. I wonder why I wrote it like that. So the domain of that function is all values except negative 2 and negative 3. So we'll take our number line, we'll chop out 2 and 3, or sorry, negative 3, negative 2. We'll write it in our interval notation, negative infinity, jump over 3, or sorry, jump over negative 3, jump also over 2, negative 2, not positive 2. So we get negative infinity to negative 3, along with negative 3 to negative 2, along with negative 2 to infinity, but not including negative 3 and negative 2. There are a couple more functions we could see. So I'll just include the definitions of them here, and we'll look at the domain of one of them. Definition. A root function has the form f of x is x to the 1 over n, where n is an integer larger than 1. So a root function, like the square root, n equals 2, cube root, n equals 3, and so on. And we can also find the domains of these root functions. And we have that as this remark. If n is odd, then the domain of f of x is x to the 1 over n, is all real numbers. You can take a cube root of a positive number or a negative number, because negatives cubed are negative, and so on. But if n is even, like a square root, remember you can't take the square root of a negative number. So if n is even, then the domain of x to the 1 over n is all... Oh, that's not right. This pocket. I usually put it in my shirt pocket, but I put it in my pants pocket then. If n is even, the domain, you could put 0 into, you could take the square root of 0. The domain of x to the 1 over n is all positive numbers and 0. So let's look at this example. Find the domain of f of x is square root of 16 minus x squared. Well, from this second remark here, well, here we have a root function with n equal 2, because the square root is, in this case, 16 minus x squared to the 1/2. So here, the domain of this function will be everywhere where the inside of the square root is greater than or equal to 0. So what we want to do is solve this. Solve 16 minus x squared. We want to set it greater than or equal to 0 by this second remark down here that I'm about to erase. So we set the inside greater than or equal to 0. Well, we solve this. What do we get? Well, we get x squared is less than or equal to 16. Numbers less than or equal to 16, so we have x is between 4 and negative 4. Larger than 4, the square will be larger than 16. Smaller than negative 4, the square will be larger than 16. But between and including 4 and negative 4, the square will be less than or equal to 16. And so we should write our domain in interval notation. So the domain is negative 4 to 4, including the endpoints. Now, all the functions we've talked about so far are examples of algebraic functions. An algebraic function It involves addition, subtraction, multiplication, division, rational powers, and roots. You can make a lot of functions using these. You can compose these together and make all kinds of functions. Like this right here is a root function composed with a quadratic function. So you could compose them. You can add these, do any of these operations on them, use rational powers, use roots. Those are algebraic functions. A transcendental function is a function which is not an algebraic function, meaning it cannot be described by basic algebraic operations like those up there. Some examples: trig functions, exponential functions, logarithmic functions are examples, some examples of many kinds of transcendental functions. And we'll actually look at trig functions next.